Hello, oceanography students. So we are going to continue with our physical oceanography series by talking about waves. So there will be two videos for this series. This first one is going to be on what waves are, how we make measurements of waves, and how waves travel through the ocean. Okay, so let's start out with the definition for waves. Waves are described as a disturbance or variation that transfers energy progressively from point to point in a medium and that may take the form of an elastic deformation or of a variation of pressure, electric or magnetic intensity, electric potential, or temperature. So that is a mouthful. So I have a shorter definition for you, and that is a wave is a disturbance which travels through a medium. Okay, so the medium would be water. Okay, so the medium will experience oscillations, but the particles that are within the medium will not travel with the wave. So it's like when you're at a stadium and you do the wave, you stand up in your seat and then you sit back down, right? And you transfer that energy to the person next to you and they stand up and they sit back down and that transfers to the next person and so on and so forth. You don't just throw your arms in the air and run around the stadium, right? Saying, I'm doing the wave, right? So that's the same thing that happens in the ocean. You'll have particles that are disturbed, and they will disturb the particles next to them, and those particles will disturb the ones next to them, and so on and so forth. And so it looks like horizontal movement, but it's really just movement of energy. Okay, so in the ocean, the waves that occur are traveling in a circular motion, and so we describe this as a circular orbital motion. As the wave travels, the water passes the energy along by moving in a circle. So here's an example of that. I'm sure you guys have all seen seagulls floating on the surface of the water, and as that seagull is sitting there on the water, a wave goes under it. So the seagull first is brought up under the wave, and then as the wave passes, the seagull then comes back down. Now, this is exactly the same thing that happens with a particle. So imagine that the seagull is just a water particle. As the energy comes towards it, it's going to be pushed up and then come back down in a circular motion, like the seagull did. Okay. Now the particle will end up slightly ahead of its original position, and that's because water moves forward faster than it moves backward. Okay. And the top part of a wave, which I'm going to get to in a second, is called the trough, or excuse me, is called the crest. And the bottom part of the wave, the deeper part, is called the trough. Okay, so water moves forward at the crest faster than it moves backward at the trough. And that's why the seagull, if you look at its original position, it's slightly ahead of where it was when it started. Okay, so here we can watch that happen. So again, the crest is the top part of the wave and the trough is the bottom part. And as the wave moves, if this video will work, as the wave moves, we see that it moves in a circle. So each individual particle is just moving in a circle, right? If there was not a wave there, it shows you the still water. So the crest is above where the still water level would be, and the trough is below where the still water level will be. But the motion is in a circle. Okay, so let's go on to some more wave terminology. So again, the crest is the highest part of the wave. The trough is the lowest part of the wave. And then we can measure the distance from one wave to the next by using a term called the wave length. And that is designated as a capital L. So this is the horizontal distance from crest to crest, or it can also be measured from trough to trough. Okay, so that's essentially, the crest is going to be the highest part of the wave, the very center of the wave. So you're measuring from the very center of the wave to the very center of the very next wave. Then we can also measure the height of the wave, and that's measured vertically. Sorry, there we go. Vertically, measuring from the trough to the crest. Okay, so you could draw that line over here as well, from the crest down to the trough. Right, so it's the vertical distance, whereas wavelength is the horizontal distance. There we go. Okay, so in this image, we can see that again, and it includes the bottom of the ocean on it. Okay, so we have a wave that's going along, and we have the crest right here as well, and then we have the trough here, the trough here, and the trough here. This dashed line represents the water level if there is no wave. Okay, so again, the crest is higher than that, and the trough is lower than that. To measure the distance from one wave to the next, we use the wavelength, which is crest to crest, so that's a horizontal distance. And to measure how high or how tall a wave is, we measure from the trough up to the crest, okay, and that's called the wave height. The depth of the water is measured from where there is no wave activity to the bottom. So that's what the D for depth stands for. Okay, additionally, we can make some other wave measurements. For example, we can measure wave steepness, and this basically tells us how steep a wave is, and it also gives us an idea of how close the wave is to breaking, or in other words, having the crest topple over. So the wave steepness is calculated by taking the wave height and divided by the wavelength. So that's basically how tall is the wave compared to how wide is the wave. And a wave will break when the ratio of wave height to wavelength is greater than 1 to 7. So here we can see in this image we have these waves, which are pretty far apart. It has a height of 4, but it has a wavelength of 200. So its steepness is just 0.02. Whereas this one, these waves have the same height, 4 meters, but their wavelength is much shorter, is only half of this one. So their wavelength is 100 meters. So their wave steepness is actually 0.04. Okay, some other important terms include wave period and wave frequency. The wave period is the time it takes successive crests or successive troughs to pass a given point. Okay, so wave period is basically how long it takes for a wave to get from one point to the next. Okay, wave frequency is the inverse of the period. So you can, if you know the period, you can calculate the frequency. The frequency is the number of wave crests passing a fixed point at a given length of time. So the comparison, wave period is the time it takes. Wave frequency is how many waves are there. Okay, so for example, if a set of waves has a period of 12 seconds, it has a frequency of 1 over 12, which means there are 0.083 waves per second, or there are 5 waves per minute. That means that 5 waves will pass a fixed point in a minute. Okay, so if you are sitting there and you start a watch, you start a timer when you see a wave crest at a specific point, and then you count how many times a wave comes to that same point, a crest passes that same point within that minute of time. Okay, and so that would be 5 waves per minute. Okay. Okay, so again, the waves are going in this direction. Okay, here's the crest, here's the trough, here's the trough, here's the crest. So the wavelength is from here to here, remember, crest to crest, and the wave height is going to be from the trough to the crest. So imagine that you are calculating wave frequency. This is the number of wave crests passing point A each second. Okay, or we can even measure it in a minute. So you sit there and you start your timer when you see the crest right at this point, and then you count and you stop your timer once you get to a minute. And that will give you how many crests, how many waves pass a point within a minute. And then you can calculate how many it is per second as well. For wave period, it would be the time required for the wave crest at point A to reach point B. Okay, so you can essentially say, okay, well, I see a wave crest at this point, and I'm going to start my timer, and I'm going to stop my timer when this wave gets here. Okay? So again, wave frequency is how frequent the waves are, how many are passing within a certain amount of time. Wave period is how long it takes for one wave to pass to where the previous wave was. Okay, so let's compare that. So I have 3 waves here that all have different frequencies. So here we have wave 1. It has a frequency of 1 hertz. A hertz is just per second, so that means 1 wave per second. Wave 2 here has a frequency of 1.5 hertz, so that's 1.5 waves per second. And then this one has a frequency of 3 hertz, so that means 3 waves per second. Okay, so clearly this has the lowest frequency, this has the highest frequency, and you can see that. You can see, you know, these waves are more frequent than these waves are. Okay, so wave 1 has the longest wavelength, and it also has the longest period, and it has the lowest frequency. Okay, so that means it takes longer, right, for one wave to get to where the previous wave was. And it also means that the waves are less frequent. Wave 2 is a medium wavelength, medium period, medium frequency, and wave 3 has the shortest wavelength and the shortest period, which means it takes less time for one wave to pass to where the previous wave was. And it also has the highest frequency, meaning there are more waves passing within a minute than compared to the wave 2 or wave 1. Okay, so where do these waves in the ocean come from? Well, there are 3 categories of waves in our ocean. We have waves that are driven by wind, okay, and we call them wind-generated waves, and that's what we're going to be focusing on in this lecture. So that essentially means wind is blowing over the surface of the water and creating waves. And those waves usually have a period up to 5 minutes. Then you have the tsunami. The tsunami is a wave that is caused by a sudden disturbance in the water. So it's caused by things like earthquakes, volcanoes, and landslides. And it's going to have a period between 5 minutes and 12 hours. And then you get to the tides. Tides are also waves, but they are waves that are caused by the gravitational pull of the moon and the sun. And so next week we'll be talking about tides. Okay, so let's talk about how wind-generated waves develop in the ocean. Okay, so over here, we'll say that this is where the wind is blowing, and our sea surface is totally flat, and the wind comes out and it starts blowing on our sea surface. What that creates are these little ripples, which I'm sure you guys have all seen, ripples on a pond or a body of water that's flat when wind blows over it. So the wind blows over the ocean surface, causing what are called capillary waves. Those are the little ripples. Their wavelength is less than 1.74 centimeters. Okay? So then, as the ripples occur, now the wind has something to blow on. So starting out, the water level was flat. There were no waves in it. So as the wind blows and it creates these capillary waves or the ripples, now the wind has something to grab onto. So it's like as if you are on a sailboat and your sail is down and then you pop your sail up, right? The capillary waves are like you popped your sail up. And so the wind is going to be able to catch more now. The capillary waves get stronger because the water catches more of the wind. Then as the wind continues, you have gravity waves that develop. The waves get larger, right? So now their wavelength is 15 to 35 times their height. That means that they are wide rolling waves. And finally, if the wind continues, the energy continues to gain, causing the height to increase faster than the length. And you have what's called a trochoidal wave developing. And that's a wave that basically has a point at the top and the trough tends to be smooth and rounded, but the crest is pointed. Okay, now eventually, once the wind speed and the wave speed are equal, the wave height and the wavelength cannot change, and the wave has reached its maximum height and wavelength. Okay, now waves don't just occur individually, right? You have wind blowing over the surface of the water. You don't just see one single ripple form. You usually see multiple ripples form. And therefore, we have multiple waves that form at a time. So instead of traveling just as one single wave, a wave is actually part of a wave train, which is multiple waves. So a group of waves of similar wavelength and period moving in the same direction across the ocean surface. And as those wave trains move, the front wave is moving into water that is flat. It's undisturbed, or it could be just opposite of what it is. And therefore, what happens is that front wave loses energy, or the energy in the front of the wave train decreases, and you basically lose the front wave. But the back wave is actually going over an area that was already disturbed by the waves in front of it. And so what you end up having is a new wave form in the back. So as you go down, as the wave train continues on, if you watch number 5 eventually becomes the beginning of the wave train, or the first wave of the wave train. Okay, so what affects how large waves get, or the energy of a wave? There are 3 factors to consider in how large a wave can be. One is wind speed. So how fast is the wind blowing? 2 is the duration of the wind. How long is the wind blowing for? Now, these 2 are wind speed and duration depends on the wind blowing in the same direction for a period of time. Okay, if the wind changes direction, then that is going to go against the waves that have developed already. Okay, so that's going to decrease the waves. So it's how long the wind is blowing for in the same direction and how fast it's blowing. Additionally, the third factor is the fetch of the wind. So that's the area over which the wind is blowing in the same direction. Okay, so we have the speed of the wind, we have the duration of how long it's blowing for, and we have the area over which it's blowing. So if you have a really strong wind blowing for a long time over a big area of the ocean, then you're going to have big waves that can develop. Okay, and this is the called the Beaufort scale, or the Beaufort wind scale, that tells you the state of the sea that develops from that wind. Okay, so we have Beaufort's numbered 0 to 12, where 0 basically means that the water is glassy and you can see your reflection in it. 12 is a hurricane. Okay, so generally, if you get to 3, then that means that you're starting to see white caps on the water. White caps mean that the wave crests are breaking, meaning the wave crests are falling over on themselves. Okay, and probably you're still pretty okay being in a small boat up to a Beaufort of 3, but above that, if you're in a small boat, then you're probably getting kind of uncomfortable. And obviously, you don't want to be out in a hurricane. And no, you don't have to memorize the Beaufort scale. Don't worry about that. Okay, now this chart is showing us what a fully developed sea could occur based on the wind speed, the fetch, and the duration. Okay, so a fully developed sea is the maximum wave size theoretically possible for a wind of a specific strength, duration, and fetch. For example, if you have a wind speed in one direction of 19 kilometers per hour, a fetch, so a distance over 19 kilometers, and it blows for 2 hours, your average wave height is 0.27 meters, and your average wavelength is 8.5 meters. Your average period is 3 seconds. So those are pretty small waves, right? But if we jump up here, if you have a wind speed of 92 kilometers per hour, you have a fetch of 2,627 kilometers, and that wind is blowing for 69 hours, you can end up with a waves that are on average 14.8 meters, 212.2 meters wide, and coming at a rate of 14, or at a time of 14.3 seconds. Now, the largest wave to be recorded or calculated was calculated in February 7th, 1933. It was calculated to be 34 meters in height, and this was on a U.S. Navy tanker. I think it's called the USS Ramapo. And a Navy lieutenant decided that he was going to use the length of the ship to calculate the actual height of the wave. So essentially what he did was when the wave was, or when part of the boat was at the trough, the lieutenant could observe when the crow's nest was in line, and he could calculate the angle over which it was on. He knew the length of the ship, and therefore he could use some geometry or trigonometry, whichever you call it, to calculate the height of the wave at 34 meters. Now, this wave occurred when there was a wind speed of 107 kilometers per hour with gusts of 126 kilometers per hour. So that is a pretty strong wind. Okay, now we were just talking about waves kind of at the surface, but what happens below the surface? So at the surface, the circular orbit's diameter equals the wave height, right? So in this image down here, we can see the surface wave, the circular orbit. The height of the wave is actually the diameter of this circle, right? Because here's the trough, right, the bottom of the circle. Here's the crest, the top of the circle. So the height is actually the diameter of the circle. Below the surface, though, we get away from where the wind is disturbing the surface. And so the diameter of that circle gets smaller and smaller the deeper you go. And that's because essentially it's transferring energy from the surface down, but it's not, energy is lost as you go down. So eventually you get to a depth at which the wave's energy is pretty negligible, meaning that you can't really feel it. And at that point we call that the wave base. Okay, so that's the depth at which the wave can't really be felt anymore. And you can calculate that using the wavelength. Take the wavelength and divide it by 2, and that gives you the wave base. Now, if the bottom of the water is down here, then that means that the wave is actually touching the bottom. If the bottom of the water is down here, then that means the wave is not touching the bottom of the water. Sorry, so as the depth increases, the motion decreases. Okay, so because sometimes the wave base is deeper than the actual depth of the water, sometimes you have the bottom that's affecting the wave. And sometimes the wave base is actually much higher than the actual depth of the water, and therefore the bottom's not affecting it. Okay, so we have different terms for waves, depending on the depth of the water that they occur in. We have deep water waves, shallow water waves, and transitional waves. Deep water waves are waves that occur in water that is greater than the wave base. Therefore, the wave's energy does not touch the seafloor, and therefore the wave is not affected by the seafloor. Shallow water waves are waves that occur in water that is less than 1/20th of the wavelength. Okay, so in other words, the wave energy is touching the bottom, and therefore the way that the wave is traveling is going to be affected by the bottom of the seafloor. Transitional waves are waves that are in the water that is greater than or equal to 1/20th of the wavelength, but less than or equal to 1/2 the wavelength. So for our understanding, we're just going to consider deep water waves and shallow water waves. Okay, so essentially, I'm going to say deep water waves are waves that occur in water that is deeper than the wave base, and shallow water waves are waves that occur in water that is more shallow than the wave base. Okay, so waves usually occur out in the open ocean in deep water because that's usually where storms occur out in the ocean. Okay, so we have winds that get created, or winds that are blowing on the surface, creating the waves. And so we have waves that develop in deep water. And therefore, these waves out here would be considered deep water waves, right? Here's the wave base, and here's the seafloor. So the wave base is much higher than the seafloor. Therefore, this wave is not affected by the seafloor. But as the energy travels, it eventually reaches the shoreline. And as it reaches the shoreline, you see that the wave's base is actually touching the seafloor now. Therefore, the energy of the wave is touching the seafloor, and the seafloor is going to be affected, or the wave is going to be affected by the seafloor. Okay, and so at that point, we would call this a shallow water wave. It occurs in shallow water. Okay, so we can calculate the speed of the wave, how fast it travels. The speed is just a distance divided by a time. So for wave speed, the distance that we use is the wavelength, and the time that we use is the period. But the wave speed really depends on the depth of the water. So for a deep water wave, the wave speed is determined simply by the wavelength. And then you also use other constants. And so here is the calculation for that. S equals 1.25 times the square root of the length in meters. So what that means is that the longer the wavelength, the faster the wave travels. Whereas with shallow water waves, the wave speed is determined by the depth of the water as well as constants like gravity. So the equation would be speed equals 3.13 times the square root of depth in meters. 3.13 and 1.25, those are just constants, okay? So what this means is that the deeper the water in a shallow water wave, the faster the wave is. Because when the wave energy hits the bottom, it will be slowed down, okay? So if the bottom is more shallow and it's farther into the wave energy, then it's going to slow down the wave even more. Now, you do not need to memorize these equations. You should know wave speed is the wavelength divided by the period, though. Okay, what you should know is that for deep water waves, wave speed is determined by the wavelength. For shallow water waves, wavelength is determined by the depth of the water. Okay, so let's talk about what happens as waves develop in the open ocean and then they approach the shore. Okay, so waves transform from deep water to shallow water waves as they approach the shore. So deep water waves, again, develop in areas of heavy wind that are usually out in the middle of the ocean. And as that wave energy moves out of the windy area, it moves faster than the wind and the steepness decreases. And because the steepness decreases, what you end up with is a swell developing. This is basically those gravity waves, those wide rolling waves. And these are made up of uniform symmetrical waves, which we will say is a wave train. So a swell is equal to a wave train, basically. Right? So if you're sitting on the beach, you don't just see one wave come up and then no more waves. You see a set of multiple waves. And that set is called a wave train. Now, because the front wave disappears, the wave train moves at half the speed of an individual wave. And I'll show you that in a second. The swell can then travel to distant shores, where the waves are affected by the water bottom and transition from deep to shallow water waves. Okay, so again, we have wind out in the middle of the ocean that creates deep water waves, and we have a swell that develops. So these are rolling waves that are part of a wave train. The swell moves closer to shore, and that transitions into a transitional wave. And then as it gets closer to the shore, a shallow water wave develops. Now we can see that the shallow water waves are touching the bottom. And what happens is, as a wave starts to touch the bottom, the front wave is going to touch the bottom first, and it's going to get slowed down, which means that the back wave can catch up to it a little bit. So as waves approach the shore, the wavelength, or the distance between one wave to the next, decreases. So as the wave feels the bottom, it slows. The wavelength decreases, and now you have the bottom pushing on it, and you have two waves that are coming together, which causes the wave height to actually increase until eventually the wave breaks on the shore. So the wave steepness increases until it reaches the 1:7 ratio and the wave breaks. Also, when the depth is about 1 1/3 times the height, the wave breaks. So you could technically sit on the beach and look at where the waves are breaking and calculate the depth of the water there if you wanted to. Okay, so again, because the front wave disappears, the wave train moves at half the speed of an individual wave. So watch this animation and you'll see the red is the speed of the wave train and the blue is the speed of an individual wave. Okay, so as it goes along, because the front wave is going away, the speed of the wave train altogether is only half the speed of an individual wave within that wave train. Okay, so that's it for this first video on waves. If you have any questions, please post them under the weekly discussion. Thanks. Have a good day.